All right, so let's look at everything that we kind of set up yesterday. So a torque is applied when there is a force that is perpendicular to the moment arm times the length of the moment arm. So that is, you've got this rod or this door, and you apply a force to it, and that force is perpendicular, and this would be R, the length of the moment arm. So if you've ever used a hammer, it's a type of lever, but it also has this moment arm, where if you move your hand further from the head of the hammer, then you get a better swing and more torque from the hammerhead. Anyway, so this force right here is perpendicular, and not all forces are perpendicular. Sometimes we apply forces, most often at strange angles. But just like when we add up forces, we can cause an object to accelerate. If we have a net torque, we can cause the mass that is distributed, the moment of inertia, that's like the rotational analogy for mass, because it's not just a mass anymore, it's a mass that has a particular distribution, and then A, the angular acceleration, is the analogy there. So remember, arc length is r theta. If we take the derivative of position with respect to time, and we take the derivative of the angular position with respect to time, that gives us a velocity times an angular speed. Velocity is equal to r times the angular speed. We can do the same thing for this velocity. If we take the derivative of the velocity with respect to time and the derivative of the angular velocity with respect to time, we get that the acceleration, the linear acceleration, is equal to r times alpha, the angular acceleration. So those three are very helpful in solving problems where you've got to relate linear motion and rotational motion, because they can both happen. Okay, so let's look at a couple of examples. All right, so let's look at a couple of examples. So my first one, I'm going to do something pretty easy here. I'm looking down on a door that has a hinge and apparently made of wavy wood. I'm just kidding. There we go. And the width of this door will be 1.5 meters, the width of the door. And here's the doorknob. And you give it a push at an angle right there at the end. I don't think it looks like it's very much at the end, but I'm definitely trying to make it look like it's at the end. So this force may be 10 newtons. And this angle right here, maybe 60 degrees. So just pretty simple little question here. What is the torque? On the door. Okay. So this force right here is not perpendicular, but it has a component. When you push on the door, you're pushing towards the door with that blue arrow that I've drawn, and along the door. And the force that's along the door is the parallel to the door component, and this force that's perpendicular to the door is the perpendicular to the door force. Pretty easy. So then the torque applied would be the force that's perpendicular times R, and my 10 newtons, but it's not all perpendicular, so I need the sine of 60. So that's the perpendicular component times the moment arm length. And I think we get 12.9. All right, let's talk about units. So I don't know that I've talked about units yet, so let's just make sure. This is a force. This is a distance. What is force measured in? Newtons. What is distance measured in? Meters. Now, footnote. Work is the force dotted with the position vector, and a dot product is FR cos theta, and that gives us a scalar. When you take two vectors and you dot product them, you get a scalar, and the scalar unit was Newton times meters, and it's the unit for energy. We named it after James Prescott Joule. Now, torque is R crossed with F. It's a cross product, which if you have the magnitude of the two vectors times the sine of the angle between the two, you get not a scalar, but you get a vector. And you get a vector that's actually perpendicular to the plane of F and R. So if I have a X, Y, Z axis, and the R is in this direction, and the F is along my negative X direction, trying to make it look three-dimensional. I don't do a very good job of that. But my torque vector is perpendicular to those. So three-dimensional. So Newton meter is the unit, and it's not a joule. All right, so let's look at another one. And let's see, here's a circle. And I'm going to apply, it's a disc. And let's say you've got a force of 10 newtons over here. You got a force of 5 newtons over here. That's equals 5 there. The radius of your disc is R is equal to 0.5 meters. And then you've got a force that is up here at an angle of 60 degrees and directed this way, and it is also 5 newtons. So what is the net torque on the disc? So first of all, do all of these forces cause the object to move in the same direction? So the 10 Newton force, I'm going to call that one number 1. This 5, let's call it number 2. And this one that's up here at this 60-degree angle business, we'll call that one 3. Okay, does the 10 Newton force cause the disc to rotate clockwise or counterclockwise? Clockwise? All right. So do you want clockwise to be positive or negative? Positive. All right, sure. So that is going to be clockwise is positive. Now, what about the 5 Newton force, this one down here, F2? Does it cause it to move or rotate clockwise or counterclockwise? Counterclockwise. All right. And then what about F3? Which way will it cause it to move? Clockwise. All right. So what is the torque then applied to this disc by force 1? Yep. The force times the distance from the center. That was 90 degrees there, so it's perpendicular. All right. Then what about force 2? Negative, Okay. And then what about this force 3? So we need the component of the force that is perpendicular to the moment arm. And the moment arm is defined as the distance from the pivot point to where the force is applied. So is the force F3 perpendicular to the radius? Yeah. Do you need that crazy 60 degrees? No. Ha ha ha. Gotcha. So be careful. So that would be also 0.5, which means that I picked a really nice one to do, and our final net torque would be 5 Newton meters. Half a 10. Did I do my math correctly? All right, let's do another one with this whole torque business. So here's another example. This time I've got a wall, and my wall is frictionless, and I have a floor, and my floor is where my ladder is propped or sits there, and I don't want my ladder to slip. So the bottom of my ladder has this grippy feet on it, and so my ladder that doesn't look very pretty here has some grippy feet here, but there's no friction between where I prop it right there. So this is no friction here, and this is 4 meters here, and not drawn to scale. This is 3 meters here, and the length of my ladder is 5 meters. And I have a person that has climbed up this ladder, and that person is right here. So the mass of the person is 55 kilograms. The length of the ladder is 5 meters. The mass of the ladder itself is 12 kilograms. And the position, I'm going to call it D for my person, he's at 3.5 meters from the floor. So the person is at 3.5 meters from where the ladder touches the floor. So this is my ladder. I'm trying to shade in blue here. There we go. Not doing a very good job coloring. But there we go. What's up? We're good? Okay. So there are a lot of forces acting on this thing, and I want to know what is the minimum coefficient of friction so that the ladder doesn't slip. Okay. Whoops, a little too far. The first thing to do is to sum all the forces, or draw the free body diagram so I can sum all the forces and put where they act. And now that our forces are not all acting at the center or on a dot, I have to take into account that the forces are acting at a distance and really analyze the torque on the system as well. Because the higher you go, the more likely the ladders to slip out from under you. So there's something to do with position and the weight of the person. Okay, so if here's my ladder, there is the gravitational force due to the earth pulling on the ladder. There's also a gravitational force of the earth pulling on the person. So Fg of the person. There's also a force from the wall holding our ladder, force normal from the wall. There's also a force normal from the floor. And then if we don't want the ladder to slip out from under us, what do we also have to have between the ladder and the floor? A friction force. So we got a force of static friction along the floor. So truly, it's a normal force from the person onto the ladder, but if the person is not moving, and the person is this climbing dude of science over here, and there is a force normal from the ladder, and then there's a gravitational force on the person. And so truly, you're right. This force right here should be the equal but opposite force between the two bodies. It should be the normal force from the person onto the ladder, but it's equal to his weight. So that's why I didn't put a normal force there. Okay? That's a good question. Equal but opposite forces, Newton's third law. Okay. So now we've got, let's see. So this is a 3, 4, 5 triangle. And I think that means that this angle is what? 53 degrees. Right? I don't think so. Okay, so once we get the angles put in here, I can actually put the angles into these forces. So the angle between the static friction force would be 53 degrees. The angle between the normal from the floor and the ladder will be our 37 degrees. The angle between the gravitational force the ladder applies, or is applied to the ladder by the earth, and the ladder would be 37 degrees. And then the angle between the gravitational force on the person and the ladder is also 37 degrees. I'm just using the hash marks because I can't write so small. And then would this be also 53 degrees? Okay. So I've got all those labeled. Now, just like we did with forces before, we have forces in the x direction. And if we want the ladder to not move, then they have to be balanced. And we have forces in the y direction. If we want the ladder to not move, they have to be balanced. And now we have forces that are acting at a particular position. So we need to sum the torque and make sure that it's in equilibrium as well. Okay? All right, so in the x direction, we've got a force normal from the wall minus the force friction static on the floor. Anything else in the x direction? Nope. All right, up and down in the y direction. It looks like we've got a force normal from the floor minus the gravitational force on the person minus the gravitational force on the ladder. Is that all the y stuff? Yeah? Okay, now we need to look at the torque. But before I do that, let's remember, where do we find the coefficient of friction? It's in the force of friction, right? So mu times the force normal. And if it's the force of friction on the floor, then I need the force normal floor. Right? And would that be equal to the force normal from the wall? Okay. Oh, look at this. Force normal floor. Force normal floor. Oh my goodness. It looks like the force normal floor is equal to the weight of the person plus the weight of the ladder. Remember, weight is another way to say gravitational force. Okay? Okay, so it looks like we're really close to having the coefficient of friction because this is a number I can calculate. I just need the normal force from the wall. So this is where we have to sum the torques. And I made a big deal about that because where you put the pivot point matters. If you want to sum the torque and find the normal force from the wall, you don't put the pivot point right there. Because what's the distance? What's the R value if the pivot point is right here and the force is right there? 0. So there's no torque on the ladder due to the normal force from the wall if that's your pivot point. Okay? If you put the pivot point in the center of the ladder, then the normal force from the wall has a distance, but also the gravitational force on the person has a distance, and the static friction of the floor has a distance, and the normal force on the floor has a distance. So there's like 4 torques you would have to sum up with angles. Now, if I put it down here at the bottom, I will have a torque due to the wall. I will have a torque due to the weights, and that's it. So that's 3. So that is the fewest number of forces that are at a distance, and it has one of my unknowns in it. So when I sum the torque, which way does if you were to imagine this ladder right here being able to rotate, being free to rotate. So here's the ladder, and the wall could push it. Which way would it rotate? Clockwise or counterclockwise? Clockwise. So here's the pivot, P, right here. What about the weight of the person? Counterclockwise. What about the weight of the ladder? Also counterclockwise. So when I sum the torque, we'll have the force normal from the wall, but not all of that force is perpendicular to the ladder. It's perpendicular to the wall, but not perpendicular to the ladder. So remember, we need the perpendicular component. So sine of 53 degrees. And it's at a distance that's equal to the length of the ladder, which was 5. But then minus the gravitational force on the person. But again, it's not perpendicular to the ladder. It's at an angle of 37 degrees to the ladder. So sine 37, and it's not at the center, but it's at 3.5 meters from the pivot point, minus the gravitational force of the ladder, and it's not perpendicular to the ladder, so I need the perpendicular component, sine 37 for that one. And it's at the center of the ladder, because isn't that where the center of mass of the ladder would be if the ladder is a uniformly made density ladder of science? Yes. So that would be half of 5, which is 2.5. And all that would add up to 0. Could you isolate F normal wall? Isn't the weight of the person going to be 55 times G? And the weight of the ladder 12 times G? And you have all these other numbers? Oh my goodness. So if you find the force from the wall, and you can find the normal force from the floor, can you find this coefficient of friction? So I'll leave that as an exercise to the students. See if you can figure that out.